Welcome back to the Science Corner. This is our series for anyone out there who's intellectually curious, and today we're doing a deep dive into something pretty foundational. The Mark I Perceptron.
Ah, yes, the Perceptron, a fascinating piece of history.
Right. It dates back to 1957, Frank Rosenblatt's work.
Mm.
And it feels like more than just history, doesn't it? It seems relevant even now with AI everywhere.
Oh, absolutely. You know, modern AI, as complex as it seems, it really stands on the shoulders of these earlier ideas. And the perceptron was, well, one of the very first concrete steps towards making a machine that could see in a basic sense and actually learn from that visual information.
Okay, yeah. Seeing and learning. Huge concepts.
They really were. It was a fundamental early experiment in machine learning and computer vision, as we now call it.
So our sources, like A Brief History of AI and Vision Systems, they frame it as a real turning point. It was a single-layer neural network, right, for binary classifications. What was the big deal about that back then?
Well, the excitement, I think, was really about the potential for automation. Could you teach a machine to tell, say, A from B, based on looking at them, even something that simple, distinguishing between two categories based on visual input? It sparked immense interest. People started dreaming about machines understanding the visual world.
Like telling cats from dogs, as you said earlier.
Yeah.
A huge leap, conceptually at least.
Exactly.
But that same source, A Brief History, it also mentions this thing called the Perceptron Winter. So the initial buzz must have faded. What happened?
Well, yes. While the perceptron was promising, its design, its architecture, had some built-in limitations. It was actually very good at certain kinds of problems.
So the linearly separable ones.
Precisely. If you could draw a straight line, metaphorically speaking, between the two categories of data, the perceptron could learn it. But it really struggled. In fact, it couldn't solve problems that needed more complex, sort of wiggly, nonlinear boundaries. And that inability to handle more complicated classifications, well, it led people to rethink things. Funding dried up a bit. The intense focus shifted. That was part of the winter.
Okay, so that sets up our mission for today, then. We want to really get under the hood of the Mark I Perceptron, understand its significance not just as this old machine, but as this core concept, right? Both its successes and, maybe more importantly, its failures paved the way for modern AI.
That's a great way to put it. Understanding the perceptron gives us, really valuable perspective on the whole journey of AI. You appreciate the breakthrough, sure, but also the hurdles researchers had to overcome.
So let's dig into that breakthrough. A Brief History says it was among the first attempts at computer vision. But the Mark I, it wasn't just an idea on paper, was it? They actually built this thing.
Oh, they absolutely built it. The Mark I Perceptron, late 1950s, was the first physical hardware realization of the perceptron algorithm. Not just simulations, a real tangible machine built for these early AI experiments.
Hardware for AI in the 50s. That's wild. The Wikipedia entry, and there's an image caption too, gives some details. A camera with a 20 by 20 array of cadmium sulfide photocells.
That's right.
That's only 400 pixels. It's kind of mind-boggling to think that was the starting point.
It is, isn't it? Especially when you think about the millions of pixels modern systems process. But yeah, those 400 photocells acted like very, very basic pixels that captured light intensity, created this simple grid of data. And that raw input then went to something called a sensory-to-association plugboard.
A plugboard? Seriously? Like an old telephone switchboard. What did that do?
Kind of. Think of it as a really manual way to connect things. Researchers could literally unplug and replug wires to connect different combinations of those 400 inputs to the next stage. It let them experiment with combining inputs, essentially creating different features from the raw pixels. Very hands-on feature engineering, you might say.
Wow, okay. And then the Wikipedia source mentions potentiometers for adaptive weights. Knobs, basically.
Essentially, yes. Potentiometers are variable resistors, like volume knobs. They allowed the researchers, Charles Whiteman was the project engineer mentioned, to manually adjust the importance or weight given to each input signal coming from that plugboard.
So that's the learning part, twisting knobs.
That was the core of its learning mechanism, yes. By tweaking these weights based on whether the machine got the answer right or wrong, they could train it. Some inputs would become more influential than others for making the correct classification. A very physical, iterative process.
Got it. And the timeline. Rosenblatt's invention in '57, then he detailed it all in his 1962 book, Principles of Neurodynamics.
Correct. That book was hugely influential. It laid out the theory, the experiments with the Mark I and other versions, and importantly, it also discussed some of the limitations they were already observing.
And it wasn't just academics tinkering, right? Wikipedia notes the CIA's photo division looked at it for analyzing aerial photos between 1960 and 64, military targets.
Yes, that's noted. It shows just how much early hope there was for practical applications, even from intelligence agencies. They saw the potential, even with this early, somewhat crude technology, for automating image analysis.
Do we know how well that worked out for them?
The sources don't really detail the success rate, unfortunately, but the fact that they invested time and resources between 1960 and 64 speaks volumes about the perceived potential, even if the Mark I itself had limitations.
Okay, so we have this physical machine, 400 pixels, plugboards, knobs,
Yeah.
making binary classifications. Let's get into how it made those decisions fundamentally.
Right. So at its core, a single-layer perceptron, like the Mark IV, is trying to find a dividing line. Imagine you plot your data points, say, measurements from the pixels on a graph. The perceptron tries to draw a single straight line to separate the points belonging to category A from the points belonging to category B.
A linear boundary.
Exactly. It calculates a weighted sum of all its inputs. Remember those potentiometers setting the weights. If that sum crosses a certain threshold value, it outputs, say, A. If not, it outputs B. Simple as that.
And the learning adjusts those weights. How did that work algorithmically?
The algorithm was beautifully simple, really. You'd show the perceptron an input, see what it outputted, and compare that to the correct answer. If it was wrong, you'd adjust the weights.
Oh.
You'd slightly increase the weights connected to inputs that should have made it fire, if it didn't fire but should have, or decrease the weights if it fired when it shouldn't have. The adjustment was proportional to the input signal and the error. It's a feedback loop, constantly nudging the weights in the right direction based on mistakes.
Wikipedia also mentions a weight vector and a bias, or W0.
Yeah.
Can you break those down?
Sure. The weight vector is just, well, all those individual weights considered together as a single list or vector. It represents the entire configuration of the perceptron's knowledge at any given time. The bias, W0, is like an extra weight that isn't connected to any specific input. It's always on. Think of it as shifting the decision line up or down without changing its angle. It gives the perceptron a bit more flexibility to find the right separation, even if all inputs happen to be 0, for instance.
Right, okay. That helps visualize the line moving. But this is where we hit the wall, isn't it? The infamous XOR problem mentioned in the limitation source. What is XOR, and why was it such a headache?
XOR stands for exclusive OR. It's a basic logic function. Given two inputs, it's true if one input is true, but not both and not neither. So true-false gives true, false-true gives true, but true-true gives false, and false-false gives false.
Okay, simple logic.
Simple logic, yes, but the problem for the perceptron is that the inputs and outputs for XOR are not linearly separable.
There's that term again? What does that mean for XOR?
Imagine plotting those 4 input possibilities. True, 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 false, false, true, false, false, on a simple 2D graph. You'd have 2 points that should output false and 2 points that should output true. Try drawing one single straight line to perfectly separate the true points from the false points.
Can't do it, can you? The truths are diagonally opposite each other. Same for the falses.
Exactly. You physically cannot draw one straight line to divide them cleanly. You'd need 2 lines, or maybe a curve. That's nonlinear separability. And a single-layer perceptron can only draw that one straight line.
Ah, I see. The limitations source mentions a logical contradiction when trying to find weights and a bias for it.
Precisely. Mathematically, you can prove that no single set of weights and a bias exists that can satisfy all 4 conditions of the XOR function using that simple linear threshold logic. It demonstrated a fundamental boundary on what that architecture could learn. It wasn't just a matter of tweaking the knobs enough, the capability wasn't there.
And it wasn't just abstract logic, right? The perceptron controversy piece mentions Rosenblatt himself knew it struggled with real visual tasks, like telling similar things apart if they were too close, or separating an object from the background.
Yes, Rosenblatt acknowledged these practical limitations in his own book. Things that seem easy for us, like figure ground separation, were genuinely hard for the basic perceptron. This further underscored that the initial excitement needed tempering. It wasn't a magic bullet for vision.
So these roadblocks, especially XOR, they really contributed to that AI winter in the 80s that A Brief History talks about. How did that failure lead to a whole winter?
Well, the failure to live up to some of the very high initial expectations combined with influential critiques highlighting these limitations like the XOR problem led to a sort of crisis of confidence in that whole approach, the connectionist approach. Funding agencies became skeptical, research funding for neural networks decreased significantly, and many researchers pivoted to other AI methods like symbolic AI for a while.
But, like you said, the story didn't stop there. The limitations source actually says that XOR, the very problem that stumped the perceptron, drove the development of multi-layer perceptrons, MLPs. Adding layers fixed it.
It did. By adding hidden layers between the input and output, you allow the network to learn intermediate representations. Essentially, the first layer might draw some lines, and the next layer can combine the results from those lines to create more complex, nonlinear decision boundaries. It gives the network the power to learn things like XOR.
Okay, so the limitation directly spurred the solution.
In many ways, yes. It forced researchers to think beyond the single layer.
And then a brief history notes this AI vision resurgence in the 90s. Better computers, new algorithms, leading to things like Viola Jones for faces, HOG, and SVMs for objects. The foundation was still useful, even with those early limits.
Absolutely crucial. The perceptron, even with its flaws, was a vital first step. The lessons learned, what worked, what didn't, why it didn't work, were absolutely instrumental in guiding the development of the much more powerful neural networks we rely on today. You learn as much from the failures sometimes.
So wrapping up this deep dive on the Mark I Perceptron, it's clear it wasn't the final answer, far from it. But it was this incredibly important early experiment. It proved the basic concept. Learning from data by adjusting connections was possible, even if that first version was, well, limited.
Couldn't agree more. And understanding why it was limited wasn't a failure ultimately. It was the key that unlocked the door to more complex architectures. It was a necessary step.
Yeah. The Mark I really serves as this powerful reminder, doesn't it? Seemingly simple ideas, maybe even flawed ones, can lay the groundwork for technologies that totally change the world.
Precisely. And it makes you wonder, doesn't it? What are the XR problems of today's AI? What current limitations might actually be pointing the way towards the next big leap forward?
That is a fascinating thought to end on. Thanks for exploring that pivotal piece of AI history with us.
My pleasure. It's always illuminating to look back at the beginnings.